Alright, this video is going to be devoted all to work. And man, I feel like I just cannot lecture about work without singing that Fergie song, Make You Work, Work, Make You Work. That's Fergie, right? The definition for work is going to be an energy transfer that occurs when a force acts on an object that moves. So the equation for work that we're going to be thinking of initially is going to be that work, capital W, not to be confused with weight, which is sometimes represented with a W as well, is going to be equal to the force applied multiplied by the displacement. Now, work itself is a scalar quantity, meaning that direction does not matter. But the other part of this that you want to kind of pick up on is the fact that we're talking about displacement. If there's no displacement, then there's no work done, thus there's no energy transferred. And we'll come back to this idea because we can also bring in some circular motion and kind of do some comparisons. But right now, if there's no displacement, meaning there's no change in distance, then there's no work done and there's no energy transferred. So again, let's think about when I decide I want to push against a wall. Instead of pushing against the wall, I decided to push a car. Let's say I'm trying to push a car and the car is not moving, not moving. Then no work is being done because there is no displacement. Just keep that in mind for the future, that because it's not moving, no work is being done. Now let's jump over to another thought. We will consider the work done at different vector quantities. So let's say we have a boat. We're looking at an aerial view of a boat. And then let's say it's pulling a water skier. And here's the person water skiing. And here's like some water kind of reacting to this water skier. And let's say that technically, if I wanted to, I could find the angle right here of my angle that I'm producing here. Now I can consider the force being applied by the boat at this unknown angle, but I really want to think about the force being applied in maybe this x component right here. And in order to find the force applied in this x component, what I have to think about is the angle. And I'm serious, there's no shame to doing the SOHCAHTOA stuff, because if I can do the SOHCAHTOA stuff, then I know that I am picking the correct angle. And so if I'm thinking about the adjacent and the hypotenuse here, I'm going to be choosing the cosine theta multiplied by the force applied by the boat. Now, this gives me the force in this x component. Well, let's go back to work. Let's say I want to find the work done in this x component. The work done in this x component then is still going to be the force multiplied by the cosine of our theta, but then we also have to think about the distance. And a lot of times for these distance problems, rather than using delta x to represent this distance, they're going to use r for radius. Now, it's the same thing. It's not that big of a deal to see the r versus the delta x value. And actually, let's make that delta r rather than just r. Are both are going to represent the same idea, the displacement in that direction and in the x direction. Now, for some of you who might be saying, right angle trig, what? We got to do that every time? And by the way, this is the equation that is in your equation packet. Let's give another example. Let's say I have a person that's sitting on a rolly chair and they're really tall apparently, and I'm pushing the rolly chair and it's traveling in this direction. I would still do the work done on the x is equal to the force multiplied by the cosine. And then in this situation then, the cosine would be cosine multiplied by 0 because really there is no angle here. And then that would be also multiplied by the change in the radius. Now this value right here for our cosine of 0 equals 1. So now we're back to the friendly equation that I showed you on the first slide, which is work is equal to force multiplied by the distance or the radius in this situation. So that angle is going to be important in some situations, but not in every situation. So don't be afraid of that angle and adding that in with my work equation. I want to ask you two questions. First, I want to ask you is, can a force like the normal force ever do work? And this is where I think you should pause the video and just think for a little bit. Can the normal force do work? Pause it right here and think about it. Maybe a couple examples in which the normal force is going to do work. I'm going to give you a second to pause. The answer here is yes. Heck yeah, I can. So there's a few different examples we can think of. We can think about something like a forklift. We can think about something like an elevator. We can think about even jumping. In all of these examples, what we're seeing is we're seeing that the displacement is in the same direction as the force. And because the displacement is in the same direction of the force, yes, work can still be done because that equation is work is multiplied by force, then the cosine of the angle, which is going to be 1 in this situation, multiplied by the change in distance, the radius. So we're going to see that the work can be done in examples with the normal force. Next, let's talk about the total work done. So the total work done, or the work total, and I always like to write totes, the work done total is just going to be the work in the one direction plus the work in the other direction plus the work really is n many times that you would like to think about work. And basically we're thinking about multiple forces are acting on an object. Now this is going to be helpful in some future problems when we're thinking about the total work done, because we're going to have to think about the total forces. There could be multiple forces that are going to be causing motion or hindering motion, and because they're going to be causing or hindering motion, we have to think about these forces and how they're going to be influencing our total work. Now before we finish this video, I would like to talk about friction, because friction is going to play a role in a lot of our conservation of energy questions and in the work done style questions. So let's go to a new slide. When you think about friction, really friction is going to be work that's done in the opposite direction of the motion. So when I think about friction, I'm thinking about work done in the opposite motion. Sometimes this is referred to when you calculate it as a negative work, or even really just a dissipative force, because it's going to dissipate the energy and that's going to be part of our total system. So really friction is going to even be considered like a non-conservative force, because it's not going to allow for the traditional conservation of energy that I see maybe in that example from the first video with the roller skater. The energy is conserved in a different way, and so let's call it a non-conservative force, because really what's going to happen is it's going to result in heat, and when it results in heat, we're going to actually see the internal molecules of the object that it's interacting with. Those internal molecules are going to become excited, and we're going to see that little amount of heat. And what's difficult is we don't actually know how many molecules. For example, if let's say I'm pulling a sled at a given angle in this direction, there's going to be a little bit of friction in this direction. And I don't actually know how much heat and how much of the frictional force is going to the box and how much of the frictional force is going to the floor. I just am able to find the total frictional force based on the situation. And going back to the non-conservative force part with this is the reason why we can say it's non-conservative is because it's not going to stay a part of the system anymore. It's actually now going to be a part of the internal energy of the object. So it was originally a part of the system, maybe with the guy going up and down the track. When he was roller skating, he was going up and down and up and down. And really what we were seeing was over time, the friction was beginning to increase, and as the friction increased, it contributed to the internal energy of not only the skateboard, but also of the track. And we are going to just count that as our total friction on the system. All right, so we're going to stop there with our work video. I'll have one more video with just an example problem on it, but I think this is a great place to stop for this.